We continue with similar work trying to deal with the permutation formula, but also trying to mimic or deal with the fundamental counting principle. For example, in how many ways can all of the letters of the word oranges be arranged if there were no further restrictions? Well, how many letters are in the word oranges? 1, 2, 3, 4, 5, 6, 7. So there would be 7 factorial ways of arranging those letters. But what if n has to be first? If n has to be first, then there's only one option for that first position. And then I take a look at the other positions. 1, 2, 3, 4, 5, 6, 7. I've got 6 choices, 5, 4, 3, 2, 1 choice. So this takes me down to 6 factorial. And you can evaluate that. You can evaluate 7 factorial, you can evaluate 6 factorial. But we're looking at some different ways of arranging. I'm going to try it with the fundamental counting principle. So that should be something we can rely on as a basis for solving. If the vowels O, A, E must be together in that order. I actually want to group those letters together. So instead of being 3 positions, the letters O, A, E count as 1 position. And then I'm left with 4 other positions for the word oranges. So I've got how many choices for those other spots? 4, 3, 2, 1. That looks like 4 factorial, but what can I actually do with OAE? With OAE, and by the way, does OAE have to go first? OAE actually doesn't have to go first, and that's why we want to group them actually underneath OAE as my choices underneath. And that's going to alter my numbers a little bit. My OAE is going to have 5 different positions where it can be, but then I've got those 4 other letters that have to fill a spot. But OAE doesn't have to be in a particular order. How many different ways can I arrange just these guys? So there's 5 factorial ways of arranging OAE with the other letters, but then the letters OAE can be arranged in 3 different ways. So I've got 3 factorial times 5 factorial. Sorry, I've been looking at lots of these problems today, and the letters OAE must actually be arranged in that way. So they cannot be rearranged. So that means the position OAE can be in 5 different locations, either at the beginning or at position 2, 3, 4, 5, and then I've got 4 other choices. The answer here is simply 5 factorial. So I've gone 7 factorial, 6 factorial, 5 factorial. Let's see what the next problem does to us. Okay, so setting this up, the letters AI must be together, but not in that order. It could be AI or IA. There are 2 different ways of arranging that. And there are 5 different places for the letters AI to go. And then I've got 4, 3, 2, 1 other letters to choose from. So my answer ends up being 5 factorial times 2 factorial, which you can evaluate. 5 different ways of arranging the letters with AI together, and then the fact that AI can be flipped around. Let's see the variations on this style. So the word kitchen. The word kitchen has 5 unique spots if I must have K, C, and N together, not necessarily in that order. So there's 5 unique first positions, 4, 3, 2, 1. But then how many different ways can I arrange KCN? The KCN is itself a fundamental counting principle That's 3 times 2 times 1. 3 choices for the first position, 2 choices for the second, 1 choice for the third. So this one is 5 factorial times 3 factorial. Now it sounds like we're getting to probability work that you may have done in the past. The vowels must not be together. Well, that's really cool. There must be an easier way. So we're going to look at the ways of arranging all the letters in kitchen. So the ways of arranging all of the letters. So that's 1, 2, 3, 4, 5, 6, 7. Choose, or 7 objects to choose from, and I'm going to arrange all 7 of them. I'm going to take all the possible ways of arranging the letters in the word kitchen and subtract the number of ways that the vowels are together. So we're getting pretty good at pairing letters together. There are two letters that must be treated as one. That's the letter I and E. And remember, it can be flipped around. Order doesn't matter. And then there are 5 other positions. 1, 2, 3, 4, 5. And I look at my choices. I've got 6, 5, 4, 3, 2, 1 number of choices. So I've got 6 ways of arranging those individual pieces, and then the 2 different ways of I and E flipping around. So it's 7p7 minus 6 factorial times 2 factorial. Can you get numbers for these last answers? So I've gone back and figured out some of those factorials. 7 factorial is 5040. 6 factorial is 720. My answer for 1C is 120. My answer for class example 2 is 240. And then if I slide down, I see the answer for these 2 questions. 5 factorial times 3 factorial is 720. And the work for the vowels must not be together is a unique one. All the possibilities, 7, arrange 7 of them. That's 7 factorial, or 5040. Minus 6 factorial times 2 factorial is 1440. The difference is 3600. So working with that idea of the fundamental counting principle, I'm going to arrange girls and boys in a row, and no 2 people of the same gender can sit together. Let's draw that out. Now I had to start with boys because I had more boys than girls, so that kind of fixed my hand there. How many boys are there? Well, there's 4 boys for the first position, 3 boys for the second boy's position, 2 boys and 1 boy. And the girls work through in the same way. What does that simplify to? It actually simplifies into 4 factorial times 3 factorial, which I'll calculate after we deal with the actors and actresses. Here's a situation where there's an and condition. And is for sure going to mean times. And here I'm not so sure I want to draw everything out. I'm going to try that P notation. I have 4 male roles, but I have 6 actors. So out of 6, I have to select 4 for the male roles. And out of the 8 actresses, I have to select 3. So I've got 2 calculations to finish off for you. So 2 answers there, 144 for class example 2, 120,960 for class example number 3. And you could write out class example number 5 like we did class example number 4. There are 4 male roles. I had 6 actors, so I have 6 choices, 5, 4, 3. That might be easier to do on your calculator, I'm not sure. And then for the ladies' positions, I had 3 female roles, but there were 8 ladies trying out. So that's 8 times 7 times 6. So I could multiply that out as well. And maybe there's an interesting mathematical pattern for you there. Remember, right now, order is important. and will continue to be so for these lessons today. So the book has done some nice drawing out for what happens when we have letters that get repeated. The word rose doesn't have any repeated letters, and actually we haven't had repeated letters. But if rose becomes Ross, then we have problems. We end up with repeated letters. And what we've shown is all the different arrangements. There are 24 different arrangements if the letters are all different. But if two of the letters are the same, I actually have 12 different arrangements. And if I change the word Ross to RSS, 3 letters are the same, I actually end up reducing the number of unique arrangements to 4. Now, that hints at a pattern, and that pattern is on the next page. The pattern on the next page suggests that when we have repeated letters, we want to divide by the repetition. So this is the number of possibilities. So letters or numbers, number of choices, and this is how often a particular one is repeated. These are the repeated values. And we need to divide by those repeated values. So when I look at arranging Vancouver and arranging all of those letters, I've got to figure out what letters are the same. And I'm going to do the same for mathematical. So the word Vancouver has 9 different letters and 2 V's. So I've got 9 factorial, divide by 2 factorial. The word mathematical has 12 different letters, but it's got 3 different repeated letters. It's got 2 M's, it has 3 A's, and 2 T's. So I have 12 factorial, divide by 2 factorial, 3 factorial, 2 factorial. I need those numbers. The numbers get a little bit large, but my calculator can handle it. 9 factorial divide by 2 factorial, and 12 factorial divide by 2 factorial, 3 factorial, 2 factorial. Now we have a kid who bought one of those mini collections of cereal from Costco, and he actually ate one already. He ate the Raisin Bran. So right now his 10 boxes of cereal has been reduced to 9. We got to be careful. So we've got 9 different choices on the top. And then we've got to figure out his repeated cereal options. There's 2 boxes of Rice Krispies, 3 boxes of Corn Flakes, which he hasn't eaten yet. So that's 3 factorial, 2 factorial, 1 box of Cocoa Puffs, that's just a single, 1 box of Shreddies, that's not repeated. Well, how many Raisin Bran did he have? There's 3, 5, 6, 7. He had 3 boxes of Raisin Bran, and he already ate one, so he has 2 left. So this is Brett dealing with 9 factorial divide by 3 factorial, 2 factorial, 2 factorial, which takes you to 15120. Check out that calculation. We've got a map question to try out, and this is the first time we've done a maps question. And the map question is kind of nice. How many different ways can I get from A to B? And the suggestion is I must always be moving closer to B. Well, how many different ways can I go forwards? How many different ways can I go forwards? There's 1, 2, 3 different ways of going forward, and there's 2 different ways of going down. That's going to form a part of my repetition. 3 factorial, 2 factorial. How many blocks will it take me to get from A to B? From A to B, it'll take me 1, 2, 3, 4, 5 blocks. So this map system gets analyzed from the outside. 5 different ways of getting there, 5 different choices, but 2 of the choices have repetition. So 5 factorial divided by 3 factorial times 2 factorial is 10. And that's it. We're going to try our work today. Good luck.